Perfect. So thank you very much, everyone, for coming. This is going to be a rant talk. Like Ken mentioned, there's a whole reason for this talk existing. But basically, I wanted to go through some very interesting points on software composition and how those things tie into security. So basically, I'm going to rant about some of the things that I think that we have had access to in software composition, in software engineering, in computer science, some of those things that we have absolutely known to be true for years and just haven't done for a variety of reasons. And maybe surface some of these things for new audiences, maybe talk through some things that folks are not familiar with, and then intro some of my favorite areas within software composition, within programming language theory, those sorts of things. And finally, hopefully, if this all goes well, considering that I put this talk together today, ties back in with the point of we can secure things via these mechanisms. Helps if I also switch to the correct window. So I will be talking through a number of different things. I basically want to walk you through why I think these things, what are the four areas there. I want to talk you through some takeaways. Like, if you learn nothing else from this talk, what can I take away from these sorts of this rant, and how can I apply them to my area of especially application security? But really, if you work anywhere now in cloud, in SDNs, in software-defined networking, any of those areas, you probably can at least take some of these things away and really attempt to understand your area and understand the things that you're working in just ever so slightly better. I'll define what I actually mean by software composition. I don't think I have a strange definition of it, but it may be a little bit more nuanced than you're used to. I'll talk through some other notables that I think of when I think of these sorts of problems in programming language theory, in software composition, those sorts of things, and also areas that you can look for these sorts of people and look for papers that I thought were interesting. And then I want to walk through four really high-level areas. I want to walk through what Grace Hopper was attempting to do when she first started studying these like software composition, compilers, how do we break down languages, how do we break down problems, etc. I want to talk through Peter J. Landon, especially the iSwim paper. If you see what I mean, is a fundamental paper, and we'll talk through why. I want to talk through what Barbara Liskov did with the Liskov substitution principle. And I want to talk through Multix. I think most people have heard of Multix. Most people have maybe seen some things about Multix. Maybe they've been curious about the historical antecedents to operating systems like Unix, but they haven't really necessarily looked into why. And I'm going to talk about what I think were the important things that we as software security folks and then the security community at large can take away from what Multix actually did. And then, because there's nothing that says logical like some hubris, I want to talk about what I think are the next 700 security tools to come. And some of these already exist. Some of these are just coming out of the research community. Some of these things are being talked about in papers. But I wanted to walk through what I think these sorts of things will do, especially vis-a-vis the four areas that we talked about today during my rant. And if you don't know me, and I've obviously been on Absolute AppSec a number of times, but my name is Stefan Edwards. I'm a practice lead at Trail of Bits. I go by a Twitter handle of Logical. You can find me on GitHub, on Lobsters, etc., all sorts of places. But basically, I work in software security. A lot of what I do at Trail of Bits has to do with programming language theory, with threat modeling, with understanding risk, with applying many of the more academic or more nuanced things to everyday software, everyday security. I usually have this sort of slide. I am very hard of hearing. I'm also from New York, but I think it'll be a little bit easier with a virtual conference and people can type things in. So, as Ken and I both alluded to, there's an actual reason why we wanted to talk about this sort of thing. Ken and I were riffing in chat, as we often do. And he said this: I want a history in software composition and the securing thereof. And it basically cascaded from there. I looked at that and I said, oh, that's really cool. There's all sorts of things we can do with that. There's a whole bunch of stuff that we can take out of this, etc. We went back and forth. And then we thought about things that maybe Ken can talk about. And then I got Heather involved, and it just exploded from there. So if we have a why for this talk, but maybe this entire conference as well, there's a lot of historical research into languages. There's a lot of historical things. And if you've seen any of my other talks, or if you've heard me rant on Twitter or other places, you've seen me talk about things that we've lost. So for example, one of the things that I always like to bring up is that I've talked with folks who maybe work at large storage companies, and they'll be working on maybe copy on write file systems. They'll be working on new ways of doing things. And I'll say, oh, you mean like what OpenVMS used to do? So there's all sorts of historical things that I, as logical, as someone who's super interested in more of the historical side of languages and the historical side of computing, actually find interesting. So I wanted to go through and take some of my favorite things in languages, in the history of computing, in software composition, and just kind of shine a light on them. But also, I really just wanted to rant. I think it's always fun when I can get up here and rant, talk about things that are interesting to me, surface a bunch of things. And if this talk explodes horribly on me, it's because I did go up here just to rant. And then obviously we can have some more fun with the comments, because we can trash talk all the things that I missed. But I think if you're going to take 3 things away from this talk, and those can be any 3 things, I would really like you to take these 3. We've been thinking about how to compose software since at least 1951. We'll talk about Grace Hopper's techniques, but there were a number of folks working in what we consider modern compilers now. This can go back all the way into the 1940s if you consider Conrad Zuse and his plan Calcul, excuse me, pronunciation is hard. But there's a number of things that we've been working on since at least the 50s that I think still apply today. And some of these things are just ways of thinking, they're modalities of processing software, but we have these historical antecedents, and I hope to surface some of these for you. And again, many of these same things that we see from Barbara Liskov, that we see from Grace Hopper, that we see from how the Multicians approach things, etc., they're directly applicable today. I'll get into it during the Multix section of the talk, but I do think that many areas that we saw in Multix, that we saw in the way that Multix was attempted to be secured, are many of the same things that you might see from TrailofBit's audit of Kubernetes, or from a modern evaluation of a new operating system. And I wanted to also surface 4 things that are maybe lesser known areas, or maybe areas in software engineering and computer science that I find fascinating, that the wider security community may not actually know. And when you hear me talking about software composition, I have a slightly spicy take. I've talked about this on Twitter before. Artem and other folks have seen me talk about this. I really don't think that things have changed all that much over the years. Niklaus Wirth had a talk, or an actual book. It's been used since at least 1976. And he talks about a very simple approach to designing programs, which is you choose a set of algorithms, you choose a set of data structures, and that combination, that bespoke mix of things, is actually what gives us programs. Now, there's obviously a whole bunch of things in there that we also have to think about. How we choose algorithms might be played up by how we model our risk, or how we actually approach other things within our application set, accessibility, user experience, etc. So there's a large number of things that we may see, but I think there are probably 3 main topics that we would want to talk about. Those are function or code composition. Basically, how do we plug in code that we've written? How do we take all of the stuff that we've put together and compose them into a simple, straightforward, and easily processed way? This also ties back into the sorts of data that we actually present to a program, present to users, to secondary systems, etc. So the way that we design our data, the way that we consume our data, etc., also plays into how we actually compose our software. very frequently when we think about software and when we think about security, we are thinking in terms of software, but we're actually discussing solutions in terms of data and in terms of consumption. So I think they actually go hand in hand. And then obviously visibility. And when I say visibility, I mean it at the programming language theoretic level. I mean it at the at the actual data hiding level, at access control, authentication, those sorts of things. Visibility is a number of things that we basically have to approach when we're thinking about how we compose software and how we actually secure it itself. So I thought there would be a very simple example of this. Most people will look at this and they will probably wonder why the hell I'm displaying this on my screen, right? We'll be looking through and seeing something that looks kind of complex. Maybe if you've seen Scheme before, you maybe can figure out what this does. But basically, Oleg Kiselyov, he's a very famous functional programmer, works in a lot of interesting areas. There was a mailing list question of how would you do an object system in Scheme? And he came back with this very simple definition. So you have a two-dimensional point. You want to define some accessors, such as a get X and a get Y. You have some setters there, so you might want to set a new X and a new Y. And then you basically have a dispatcher. Now, if you think about this, that's all you really need to do in order to have an object system. You need some mechanism for holding your X and Y. You need accessors for it, right? We can get the X and Y out of an object. And then we basically hide it all. We hide visibility to this entire thing through a lambda, through a closure itself. So we enclose on an environment. We hide X and Y. We allow users to introspect those things via accessors. And then we basically give them a mechanism for signaling when, hey, maybe you've actually done this sort of thing. Now, this is fairly complex. I think most users, if they were presented with software that looked like this, they would probably run away screaming. And that's usually the case when we have these sorts of like abstraction breaks or issues with the way that we define things. Now, I chose something else. This is another semi-esoteric language. Not everyone works in this language. And this language is OCaml. But I think most folks who have some background on programming languages and have some understanding of the way that classes and data structures and data hiding works can read this and understand what we're doing. We have a two-dimensional point object. It takes two parameters, X and Y, and then we define methods for those and types. So we know that X and Y are floating point numbers. They're basically decimals. And we know that we need accessor mechanisms for this X and Y. Now, in terms of software composition, they actually achieve exactly the same thing, right? When we want to define something in Scheme, and if you were actually writing in Scheme, please don't use the example that I used here. There's all sorts of better ways of doing this, like SRFI 57. But you can use these things, right? We have a data structure with 2 points. We know how to access those sorts of things. And those things are not actually accessible outside of the scope or the visibility that we've defined. If you think about it, if you wanted to modify how the Scheme system worked, you could easily change the visibility. You could easily change the scope. And you could make sure that certain things actually work in different ways there. So there's a number of things that we have that we absolutely can control. However, the mechanisms of doing these are very different. Scheme uses a closure. There's some dispatch. It uses symbols. We use environment capturing. Basically, we use binds to capture the X and Y values. We use those closures, capture them in the environment. And whilst the OCaml is probably not familiar to everyone at the conference, or it's not the most the most common mechanism for defining these sorts of things, if you have a background in Java or Scala or Ruby or any of those sorts of languages, you can look at that and mostly understand what it's doing. And indeed, we actually have very different mechanisms for using these sorts of things in some ways, right? In terms of the Scheme system, we get an accessor and we provide it with a symbol to say get X, right? We have some foo, we define a make point, and we pass this in. And then in OCaml, we actually have a very simple accessor itself. We just say pound X, that gives me the X value, or pound Y, give me the Y value, right? So we end up with exactly the same semantics of what we want via very different mechanisms. Now, there's an interesting difference between the two of those, right? The way that we have these, the way that we define things in our languages actually shapes the way that we use them. I know this is sort of getting towards Sapir-Whorf. This is sort of getting through some things that are, you know, a little bit more tenuous. But basically, the things that we provide to users via our languages or via the tool sets that we provide actually shapes the way that users use systems. You absolutely can have an object system in Scheme. You use a series of closures, you provide things back, and now you have an object system. Similar to JavaScript, how many of us have seen prototypical inheritance in JavaScript, seen things that try to break prototypes and make them into, make them into a class system, because that's the sort of tools that you have. And the things that we provide in our languages influence the way that we specify software, the way that we test software, and even the tooling. If you think about it, if I accidentally change this to get M, the Scheme compiler itself would have no mechanism. There obviously are ways of doing this, but the Scheme system would have minimal mechanisms to actually understand that I mistyped get M and now am going to have a runtime error within the system because I have processed this. However, if I change this to M, the Scheme system, the OCaml system absolutely at compile time knows that this should not be an M, and that this will actually fail and can warn me about it. So the languages that we provide actually influence the sorts of toolings, the sorts of tests, everything that we can do about it. And my spicy take to this is that most security actually falls within these boundaries. Now, I am obviously going to expand on that, and I think there are more things out there than actual program analysis or those sorts of things. But I think most things fall into, we have issues with specifications, we have issues with testing, and we don't have tools to actually process and handle those sorts of things. And we are not, as security people, as programming language theorists, actually providing those sorts of things back to developers to actually use. Now, I thought this was funny. I tweeted about this on Twitter, but as I was researching this talk yesterday, as I was writing this talk today, I ran across this blurb in the Univac programming manual. So this is from 1953, and I absolutely love this. And it says, the programmer must be adamant in requiring a complete description of the problem, of the input data, of the form and volume of the desired output data, as well as of the computational or processing steps to be performed. Now, if you're a programmer, if you're a security person, if you're anyone who deals with computers at all, when was the last time you had any of those things? Yeah, and yes, at Trail of Bits, we obviously work with clients who do have those sorts of things. So it's not necessarily so different from my experience. But when I worked at previous companies, when I've worked on certain projects, even here at Trail of Bits, it's very clear that we do not have complete problem descriptions. And that's not a developer failing. That's not a business failing. That's a holistic failing that we're not providing these tools, and we're not providing things to actually do what the Univac manual here calls problem analysis. And obviously, this talk is very LangSec focused. I am absolutely 100% guilty of being in LangSec, of thinking about things in a language security theoretic way. I understand these things. And I'm not trying to advocate that every single problem is a nail, because all I do is look at things as a language security hammer. However, what I am saying is that I do think many of these problems stem from the same root, and we do have processes for handling these. And I do think LangSec, or things that focus in that approach, do have some of the answers that we might want and need. Now, there's a number of things that I can't rant about during this talk. I think there's a number of things that are extremely interesting. John McCarthy is fascinating to me. If you're interested in the history of programming, or if you've dealt with protocols, you've worked with John Bacchus's work a number of times. I think there are some notables in this list, however, that folks are not nearly as familiar with. Frances Allen, she wrote one of the seminal papers on compiler optimization, on program optimization. And to this day, I would say you could probably get 70 to 80% of a modern optimizing compiler from the work that Frances Allen laid out in the 70s. So there's a large body of work that allows you to get fairly decent optimization results from a paper that most people have not read. Margaret Hamilton, she was the Apollo lead. There's a number of interesting things that she did in her work during the Apollo program to actually compose software, and the way that NASA works is incredibly fascinating. Going down to the line and the reason why a bug was entered, that all started with Apollo and then later was actually brought in as part of this language down here called HAL-S. And another interesting luminary on this list is Luca Cardelli. If you're interested in programming language theory, it behooves you to read a large number of things that Luca has written. He is one of the kindest people that I have actually interacted with on the internet. He helped me when I was a small child just getting interested into programming language theory. I asked him all sorts of stupid questions, but he also wrote a number of seminal papers on compiling ML and compiling languages like Oblique and Modular 3. And they're extremely fascinating if you're interested in the history of compilers, if you're interested in the way that things work. It behooves you to read everything that Luca Cardelli has worked. And then obviously there's a number of other luminaries here. If you're familiar with the history of Unix, etc., you know most of these folks that are here. My other favorite here is if you have a chance to read what Tony Hoare considers his billion-dollar mistake. So let's talk about Grace Hopper. I think most people are very familiar with Grace Hopper. She is a luminary in the programming world. She did a number of interesting things, but she's obviously famous for bringing COBOL to the front, right? And COBOL is a business language. It's often derided, but at the time that Admiral Hopper was actually working on COBOL, there was a real reason why we were doing these sorts of things. I'm not going to actually focus on that so much. I want to focus on what is called the A0 system. A0 is actually a set of languages that Grace Hopper worked on, and obviously teams within the Navy, within IBM, within a few different places at RAND, etc., worked on. But basically, these were the first steps towards modern compilers and actually understanding user experience and developer experience when working with low-level systems. Now, A0 was basically written in 1951, and it allowed a very simple thing. It allowed someone to no longer have to remember how the Univac worked. If you haven't researched Univac, it's actually fascinating. Univac did not use binary directly. It actually used a thing called binary XS3. So if you wanted to encode the number 1, you would take 1, add 3 to it, end up at 4, and now you have what Univac actually used for binary. So if you're programming at that level for the Univac for systems of the similar vintage, you were literally writing octal, you were literally thinking in binary and coming up with ways of encoding these sorts of things. And Hopper realized that this was an incredibly painful way to work. And so she started on a series of simple abstractions with A0 to actually fix those sorts of things. Now, this is a comment from Jean Semet, also another great computer scientist. But what Jean is pointing out here is what Grace Hopper did in Flowmatic, which was B0, and other languages, was basically to realize that there was a common vocabulary that developers were using and then not able to codify into the languages that they had at the time. So if you take anything away from Grace Hopper's work, her history, etc., it would be this, that there is a large number of things, and that level of abstraction is what we need to find and what we need to pinpoint. Now, she worked in a very restrictive environment, right? Univac had XS3. You needed to use 9's complement to codify things. We had to map decimal to binary for any single operation, codify things to use octal, etc. Or, and this is crazy, we could write something that says, hey, compare product number of A with product number of B, and if A is greater than B, go to 10. So no longer are we trying to think of, the comparison operation is actually this one, and we have this location. And remember that we actually need to encode 10 with 9 complement and XS3 notation, etc. Now we can just say, compare these two product numbers, and if one is greater than the other, go to number 10. So if we take anything away from what Grace Hopper did, what we were thinking about here, it's this. We need precise abstractions. And I know that sounds strange, right? How can you abstract something precisely? But there are mechanisms for actually understanding what your users, what your developers, etc., actually are doing with your languages and actually are doing with your systems. And then we can actually encode those in an abstraction that allows us to actually precisely understand what's going on here. And this simpler mechanism, this simpler case, actually allows us to surface bugs faster. We have a mechanism by which we can actually see things in a simple environment, and we can obviously read the code much faster because it's written in English here. But if you know and you're a subject matter expert, you can actually work through these things in a simpler fashion. And it led obviously to many advancements within the space itself. Now, I also want to talk about Peter Landon. He also programmed the Univac, and of the two people, he's Grace Hopper and Peter Landon both worked on Univac. So that's an interesting thing to note, I think. But Peter Landon also created a large number of things that we in programming language theory, in spaces that touch programming language implementation, probably have some level of familiarity with. So if you've ever heard a programmer define something as syntactic sugar, that was actually defined by Peter Landon in a paper called the shape of the next 700 languages to come, or the next 700 programming languages to come. And this is very often called the ISWIM paper. And that's what I want to focus on here. So my spicy take is that ISWIM should effectively be required reading. And this is a paper from 1966. And within 10 pages, he defines an abstract machine. And abstract machines are basically simpler computers that allow us to review them, to work through the actual semantics of what a program is, etc. He defined this very simple machine called the SCCD machine. He also defined what in modern parlance we would consider an intermediate representation, basically a mechanism for transiting from what the program semantically means and what the syntax of the program is. There's a few other steps in between. He also defined a new mathematical-like syntax. And if you've seen languages like Haskell or Standard ML or OCaml, those sorts of things, they actually trace their lineage back to what Landon was doing in the ISWIM paper. And he also defines the correspondence between what we write, what we physically write, the textual review of ISWIM, all the way through to the end resulting program semantics in about 10 pages. And there's also some interesting commentary back and forth between Landon and several other famous computer scientists at the time. But basically, within a 10-page paper, he's defined many of the things that we today take for granted when we're working in programming language theory. So why is this actually interesting to us? SCCD defines a very simple machine that's easy to target and easy to analyze. So if I am working as a developer and I wanted to work on a new programming language, or I wanted to analyze a new language, I could compose to SCCD, and now I actually have all of the tools that work with SCCD, all of the understanding, my mapping of semantics, etc., to this simple machine. I now have that abstract level, and I can go from there. And I say this as someone who has actually done this. If you've ever seen any of my work in digamma, it actually later targets an SCCD machine because I was trying to analyze it in a similar fashion. He also worked on a mathematical syntax, which was easier for subject matter experts to write, right? If you're familiar with the way that mathematicians use like the where clause or those sorts of things, Peter Landon noted that mathematicians and folks who work in maths actually would want to write, and then made sure that there was a syntax that actually transited that way. And then he also worked on a clear transition between all of these states, and honestly made one of the first real functional languages and its application. If you read the paper, you'll note that he says that there's a few industrial things. But what I thought was interesting was actually the conclusion. Obviously, there's a whole set of things here, but Peter Landon actually goes through that through the process of understanding how we communicate with computers and how that ties in to the way that we analyze our programs, the way that we physically write and store our programs, and then actually go through the processes of transitioning from this high-level representation to machine level. And obviously, I don't want to spend time reading through this, but I do think that this is the meat of what is interesting about iSwim. There's so many interesting things in a small, very easily understood 10-page paper that you can go through and actually start to understand what was being done here by one of the most famous computer scientists in programming language theory. So if you take anything away from Landon, or if you're interested in the sorts of things that I'm thinking for Landon, I think what we actually need is a clear method of composing and decomposing software. That's it. Landon laid out and defined a large mechanism and a large body of things that we can actually start to understand and decompose our software with, and then actually take those better definitions and better tools and start to understand our flow of correctness, our flow of program semantics, etc., just from these very simple rules that he defines in the iSwim paper. Now, Barbara Liskov did not program the Univac. She's just slightly after that age group, but she actually was fascinating for a number of areas. Obviously, she is also one of the first women to earn her PhD in computer science in the United States in 1968. She worked on very early OO languages. So if you're familiar with the history of programming languages, she worked on Clue. She worked very closely with John McCarthy. But the thing I'm interested in is actually what's called the Liskov substitution principle. And we'll talk about this. But the Liskov substitution principle is effectively a subtype relation. And I don't want to get into what that actually means, but basically Liskov understood that there was a mechanism by which we can actually take a very simple set of rules and tie these rules together in a subtyping arrangement such that we now have a relationship to Hoare logic, which is a mechanism for actually understanding software and processing the actual requirements of what a function may use, etc., or similar construction to what Bertrand Meyer had worked in with his design by contract. So we have this very simple substitution or subtype relationship that most folks can understand. And now by tying those two together at a tight theoretic level, we actually can see a number of things here that are extremely fascinating. So what do we actually get from this, right? We are now able to understand and approach from the OO level, from the object orientation level, or from a Hoare type theory level, or those sorts of things. We can actually understand the actions that a supertype allows and the actions that a subtype allows, and then start to analyze and decompose our software in that way in order to better understand what we're actually looking at here. And I found this as an interesting example here. We have a superclass of bird. We have a set of actions that maybe flying birds can take, but then we also want to have things that maybe cannot actually do what flying birds can actually do. So this is a fascinating decomposition, but still based on the way that object orientation works, that extensions work, abstract types, etc. work, we now know based on Liskov's substitution principle or subtyping relations, we actually know that we can use ostrich anywhere that we can accept birds. we can use ducks anywhere that we can accept birds, but then we also cannot use ostriches in anywhere that we would want a flying bird, because an ostrich is not a flying bird based on the rules that we set up. So we have a general concept that is extremely simple, and yet we can take that and codify many different things there. We can codify correctness of access, we can codify correctness of actual use, modulo some notions of decidability, and there's no real theoretical underpinnings to this that are complex to the normal user. You could show this class or this series of classes to almost any Java programmer, and they would effectively understand why you were doing these sorts of things and what the breakdown is here. So Liskov and the substitution principle actually brought us to this. Now, the last area in the history of software composition that I wanted to surface was Multix. Multix is the predecessor to Unix in some ways. I'm sure Unix Ninja and some other folks would take umbrage with this, but the folks who were working on Unix originally were working on Multix and then wanted a simpler system. And Multix is basically a mechanism for providing utility-like computing systems. Some might even say cloud computing systems. I will definitely take that spicy take. But basically a mechanism for having these sorts of things within a single operating system from effectively 1969. Now, there's earlier antecedents to Multix. It started out in 65 with definitions, but basically by 1969 and later by 1974, we had many of these things available in a simple system. Now, think through what Linux is. Think through what modern operating systems are. These were pioneered and started mainly in Multix. And there was even, and if you're interested in the way that we relay security findings and we relay security processes, it behooves you to actually read this Multix security evaluation vulnerability analysis from the Air Force Tiger team, which we now would probably call a red team. But there was a series of evaluations against Multix and its security, and this was fed back in a security engineering loop. So if I wanted to have a spicy take on this, and I obviously am known for this, it's that I'm putting forth this like 10th rule of cloud computing, which is a spoof of Greenspun's 10th rule. But I really do think that every cloud computing system is effectively an ad hoc, informally specified, etc. system of half of what Multix provides. And if you really think about it, Multix was aimed at providing utility computing servers with secure definitions written in high-level languages, with security evaluations by cool people, and it's effectively Kubernetes, or what we see in GCP, or any of these sorts of things. And it codified a rich environment for sharing, for actually processing data with strong security and a built-in database, right? The entire system was underpinned by a secure relational database called MRDS. And these are all things that we struggle with today, right? Think about how often you want to talk about something and you're thinking about mandatory access control versus maybe role-based access control. You need instrumentation, you need auditing, you need ease of access. Multix actually handled all of these things in the late 60s and early 70s. And yet we don't talk about the way that Multix did it. And if you are going to look into these things, I do think it behooves you to review what Multix did so you don't repeat some of their mistakes. Now, why did I talk about all these things? And obviously, I'm butting up right up against time here. But if you start to look at these sorts of things, and my hot take will be that we're going to have holistic, misspelled environments that actually allow us to process these sorts of things and really no longer separate out specification, language, data, etc. These things will start to coalesce into single tools so that we're no longer attempting to look at what does what does this look like under this specific environment. We're starting to look at these sorts of things holistically from the almost a program analysis fashion. We're not separating out the sorts of things that we're doing out into different things. And I think systems like cyber reasoning, like symbolic executors, especially as we add things such as fuzzing and whatnot to symbolic executors, we'll start to see more systems that are spread out and applied more widely, such as those sorts of tools here. And I go through and I actually decompose these. I know I'm right up against time, but I do think that we need to, with each one of these, with Hopper for understanding our precise abstractions, for going into actual designs, to Landon with simple, very simple tools and a very simple mechanism for mapping our current environments through to those tools, to what Liskov does with more type theory and more tools for these sorts of things and more specifications, and to all the way to the multicians, that we have these great environments, we have these holistic environments, and we need these rigorous definitions and security guarantees and things like Zelkova or other mechanisms by which we can start to analyze and really struggle with our environments from a holistic and centralized fashion. So obviously I'm right up against time. That was the end of my rant. I can take questions via Twitter or via Slack. But thank you very much, everyone. It was an absolute pleasure here. And I will switch back.